In this tutorial, we are going to discuss how to find the approximate solution of system of linear equations using Gauss-Seidel method. Let's consider the general form of system of linear equations where these a's and b's are known numbers and x are the unknown numbers which we need to find using this method. In order to apply this method, the system must satisfy three conditions. First condition is that it should be a square system. It means that the number of variables should be equal to the number of equations. Second condition is that it should have a unique solution, and third condition is that the leading diagonal entries of the coefficient matrix must be non-zero. The leading diagonal of the coefficient matrix is the diagonal from top left to the bottom right. If these three conditions are satisfied, then the solution of the system of linear equation can be found using Gauss-Seidel method. For example, here we are given 3 by 3 square system. If we assume that it has a unique solution and the leading diagonal entries a11, a22, a33, they are non-zero, then we can find its approximate solution using this method. The algorithm of this method says that we need to find the solution expression of first variable x1 from first equation, solution expression of the second variable x2 from second equation, and solution expression for the third variable from the third equation. The next step is to write the Gauss-Seidel iterative scheme. So this is how we write the Gauss-Seidel iterative scheme. On the left hand side superscript we have written I plus 1, and you can figure out that to find the I plus 1th approximate solution of x1 we need ith approximate solution of x2 and x3. To find the I plus 1th approximate solution of x2 we need ith approximate solution of x3 but I plus 1th approximate solution of x1, which we just found in the first step. To find the I plus 1th approximate solution of x3, we need I plus 1th approximate solution of x1 and x2, which we just found here in the first and second equation. So the basic idea is as soon as you get the value of the variable, you will utilize it in the next in the evaluation of the next equation. In specific, if we put I is equals to 0 into this system, we will get the solution expression for the first approximate solution. On the right hand side, you can see that for evaluating the first approximate solution of x1, you need initial solution of x2 and x3. To calculate the first approximate solution of x2, you need initial approximation of x3 and first approximation of x1, which we just found from here first equation. To find the first approximate solution of x3, you need first approximate solution of x1 and x2, which you have just found from first and second equation. For I is equals to 1, you will get the solution expression for the second approximate solution, and on the right hand side you can see that you need first approximate solution of x2 and x3 to calculate second approximate solution of x1. You need first approximate solution of x3 and second approximate solution of x1 to find the second approximate solution of x2. Similarly, you need second approximate solution of x1 and x2 to find the second approximate solution of x3. We continue this process until we get two successive approximate solutions same. Now let's consider an example and see how this algorithm works. This is a 3 by 3 system. Here we can see that the leading diagonal entries, which are 5, 9, minus 7, they are clearly not equals to 0. If we assume that this system has a unique solution, then we can apply this method to find the approximate solution. Algorithm says that we need to find the solution expression of x1 from first equation, x2 from second equation, and x3 from third equation. So this is how we write these solution expressions. The next step is to write the Gauss-Seidel iterative scheme. So this is how we write the Gauss-Seidel iterative scheme. We need ith approximate value of x2 and x3 to find I plus 1th approximate value of x1. We need ith approximate value of x3 and I plus 1th approximate value of x1 to find I plus 1th approximate value of x2. Similarly, we need I plus 1th approximate value of x1 and x2 to find I plus 1 approximate value of x3. If we substitute I is equals to 0 into this scheme, we will get the solution expression for the first approximate solution. On the right hand side, for evaluation of x1 we need initial solution of x2 and x3. If we assume that the initial solution is 0, 0, 0, then x1 can be computed as minus 0.200. To calculate x2 we need initial solution of x3 which is equals to 0 and first approximate solution of x1 which we just found here in the first equation which is equals to minus 0.2, which we will substitute this value here, and the result of x2 becomes 0.156. To calculate the first approximate value of x3 we need first approximate value of x1 and x2 which we just obtained from here. We'll substitute minus 0.2 and 0.156 in this place and in this place. So the value of first approximate solution of x3 is equals to minus 0.508. Similarly, for I is equals to 1, we get the solution expression for the second approximate solution, and substituting the corresponding values we'll get minus 0.167, 0.334, minus 0.429. Similarly, if we substitute I is equals to 2, we get the solution expression for the third approximate solution. Here I have calculated the approximate solutions up to fifth iteration. You can notice that the first variable x1 is approaching to 0.186, the second variable x2 is approaching to 0.331, and third variable is approaching to minus 0.423. And you also notice that the values, the approximate solution in fourth and fifth iteration are same. So we can stop this iterative process here and consider the approximate solution obtained at the fifth iteration as our required approximate solution. We can also check whether this solution is correct or not. So we'll substitute these values into the original equations and see whether the left hand side is equals to right hand side or not. Here you can figure out that the expression 5x1 minus 2x2 plus 3x3 is equals to minus 1.001, which is equivalent to the right hand side minus 1. Similarly, second and third equation are also satisfied approximately. Hence we can say that the solution obtained here is our good approximate solution.